Any questions about what we did yesterday or before? All right, so what reactions did we do yesterday? We did HX, H plus H2O, and we did H plus and the alcohol. So a lot of those are pretty similar in terms of mechanisms. The ones we're going to do today are a little bit different. And as we go, I'll give you some more ideas about Regio stereoselectivity. Probably Monday when we come back, we'll talk a little bit more about sort of hard and fast rules that we can use, like yesterday's carbocation. If you have a carbocation, the reaction is not going to be stereoselective. If you have a symmetrical alkene, you're not going to have Regio selectivity. So we'll begin to kind of hone down on those rules. But the first reaction that we'll talk about is bromination. And so for bromination, what we're going to do is we're going to take a double bond and we're going to treat it with Br2. So we're going to have two Brs that we're going to add across the double bond. So question number one, what gets added across the double bond? Two Brs. Now that automatically means that the reaction cannot be regioselective. Because whether I add the Brs this way or this way, I'm going to get the same product. So anytime you have a symmetrical alkene or a symmetrical reagent, the reaction can't be regioselective. And then we'll talk about whether it's stereoselective or not in a few minutes. So first of all, you might say, okay, Br2, I don't see any positive charge there. Double bond we know is a nucleophile, so how's this going to work? Remember that there is, in the pi bond, there is that cloud of electron density. What happens is that when the Br2 molecule gets close to that cloud of electron density, it polarizes. So one of the bromines becomes delta plus and the other one becomes delta minus. And that happens when it gets close to the double bond cloud of electrons. So when it does that, those two Brs are going to break apart. And so we're essentially going to add a Br plus to the double bond. So we're going to end up with one of the carbons, the Br adding to one of the carbons, and then the other carbon becoming a carbocation. And then I still have my Br minus now. Now the difference here is that the Br is large enough to actually fit over both of the carbons, to sit over both of them at the same time. So what we really end up forming is this triangle where those two carbons now share the positive charge. So it's going to delocalize. So it's going to delocalize the positive charge. And that's always a good situation. Right? If we can get two atoms to share the positive charge, that's better than just having one. So hydrogen can't do this. Only atoms that are large, like bromine. And then there'll also be another one that'll do this, mercury, that we'll talk about next week. So this is the first one that can form a triangular intermediate. So now I'm sitting with the Br minus, and the Br minus has to add to the carbon. But when the Br minus adds to the carbon, it has to add from underneath that three-membered ring. It cannot add from the top. So the Br minus adds underneath, and then the bromine removes its partial bond and goes to bond to the other carbon. So this is kind of like backside attack. It's not kind of like it is, but it's not in the true context of SN2. So the Br minus has to add from underneath, and what that means is that the two bromines always add 100% trans because of the triangular intermediate. And the reaction is not going to be Regio selective because it doesn't, for the moment, it doesn't matter where the bromine's added because it's two bromines of the same atom. And so the question is, could this reaction be stereoselective? Yes, it could be. When is it going to be? Well, when it generates two different stereoisomers. And that'll happen when we use it with rings. All right, so that's the basics of bromination. So for the next reaction, let's go ahead and do this with like cyclohexene. And when we do with cyclohexene, now I have a ring. So there is going to be a difference between the bromines adding cis and the bromines adding trans. So if we take our cyclohexene ring, here's how we would typically write that mechanism. I would take the pair of electrons, move it to one bromine, and then break the bromine-bromine bond and throw the electrons to the other side. And that's going to form this bromonium ion. Both carbons are going to be slightly positive, and I'm going to end up with a Br minus. And you may, the other thing with this reaction is I'm not writing transition states for this reaction, and I'm not going to. Because the problem here is the transition with the dotted partial bond to the bromine, that's going to get totally confused with the partial bond of the transition state. So I'm not going to draw transition states for this particular reaction. The other ones, yes, we could write transition states, but for this one, no. Okay, so then the bromine comes and adds from underneath the ring, and the other bromine goes to the other side, so that the product that I make has one bromine, let's say, added to the top, and the other bromine added from underneath. So I get 100% of the trans 1,2-dibromocyclohexane.
It could add technically like from the top, the other one goes below.
It could add from the bottom and the other one add from the top. So what's critical is it's a Bolden dash wedge. So it's the idea is the major product here, well actually the only product is trans. So you could easily have that would be an acceptable product too. And actually the relationship between those two is that they are what kind of stereoisomers are those two? They're enantiomers because both carbons are opposite. So they're enantiomers. And then going back to yesterday, unless I use a chiral reagent, I'm always going to get a 50-50 mixture of enantiomers. Okay. But the critical part is it's 100% trans. So now let's take a look at this from stereo selectivity. Number one, to be selective, you need more than one product. So this is where the rules about possible products comes into play. The trans is one possible product. The other possible product is that the bromines add cis. So whenever we're looking at possible products, we're thinking, okay, I've got two groups. I can add them to the double bond one way, reverse it. That's two ways. That gives us the possible products for Regio selectivity. And then when I add those groups, 100% cis and 100% trans, that gives us the possible products for stereo selectivity. And the critical part is, are those products different? Because if I add cis or trans and I end up with the same product, I can't be selective. Same thing's true for adding Markovnikov, opposite of Markovnikov. If I only get one product, can't be selective there either. Okay. So in this case, I've got 0% of the cis, but the question is, are those two different products? Yes or no? Are those two different stereoisomers? They're not the same. They're not the same, they're different, and what's their relationship?
Those are enantiomers and those are diastereomers.
So these were enantiomers and these are diastereomers. So they're two different stereoisomers. I'm not getting the same product when I add 100% cis and 100% trans. Now, this goes back to what I said yesterday about one of the sort of weird things about selectivity. Selectivity doesn't make any difference whether it's 51-49 or 100 to 0. There's no special term that's used if it's 100 to 0. So in this case, it's just as selective as if it was 51-49. So we have two possible stereoisomeric products. The reaction has chosen one over the other. Therefore, it's stereoselective. So this reaction is stereoselective. Is it regioselective? No, because I've got a symmetrical alkene and a symmetrical reagent. So there's no way it can be regioselective. So that's bromination. And that's a mechanism for bromination. Okay. Since I'm adding two bromines, there's no Markovnikov or anti-Markovnikov here. Well, technically there's no Markovnikov or anti-Markovnikov because there's no H to go with the carbons that have hydrogens. So two bromines, it's not Markovnikov or anti-Markovnikov, 100% trans. Those are the three characteristics of this reaction. All right, everybody with me?
Sorry, can you put that again? You said it's 100% trans, no anti.
Right, so the two things that we're adding are, we're adding two BRs. There's no Markovnikov or anti-Markovnikov that we have to worry about. And then it's 100% trans. Those are the three characteristics that for this reaction. So now what I get to do is now I'm going to change this reaction a little bit. And I'm going to change it a little bit more. And when I do that, I end up with a different problem. So let me start with my cyclohexane and say, I'm going to add Br2 and water to it. So this is what's called bromohydrin formation. It's going to form a bromohydrin. And so in this reaction, I'm going to add a Br and an OH across the double bond. So the bromine is going to act as the electrophile. The Br plus is going to act as the electrophile in this reaction. So I'm going to start it out the same way. I'm going to say, okay, I'm going to take my double bond. I'm going to use a pair of electrons to bond the bromine and kick off the Br minus. And so that's going to give me my bromonium ion. I don't know if I've said that yet. This is called the bromonium ion. I should probably have started out with that. That's what it's called. So I form my bromonium ion. And now the water, well, and I've got a Br minus, and then I've got an H2O. So now I take a step back from this reaction and say, okay, when I formed the triangle with just Br2, the Br minus had to swing around the triangle and attack from underneath. But there wasn't anything else there to compete with it. Now if I'm using bromine in the solvent water, so there's a lot more water than there is bromine, what happens is once you form the triangle, there's a water molecule right there waiting to add. So the Br minus never gets a chance to swing around and add. By the time it would get there, the water's already added because it's the solvent. So now the water's going to attack either one of those carbons in this case. So the water comes in, attacks, the pair of electrons goes to the bromine. I end up with the bromine maybe adding from the top, and I end up with the water adding from the bottom. And again, whole water molecule adds. Now I'm going to lose the H plus. And I'm going to end up with my bromohydrin, which is the Br and the OH adding. This was also 100% trans. So is this reaction stereoselective? Yes, because the other possible product is cis. So this reaction is stereoselective. Regioselective? Why not?
Isn't it like a symmetrical?
The alkene's symmetrical. Even though the reagent isn't, the alkene is symmetrical. So this is not regioselective. So now I've got a bromohydrin. I can form my bromohydrin. Later on, we'll find out bromohydrants really only kind of have one use, and that's to make epoxides. And we'll learn about what an epoxide is later. But now I have well, first, everybody kind of with me still? So now the issue is, what if the alkene is unsymmetrical? The only reason this reaction wasn't Regio selective is because the alkene was symmetrical. What if I change this reaction and just do this? I'll put a methyl group on one of the two carbons. And you could always go through on the video, and I haven't been uploading the PowerPoint slides that I write to kind of cut people off from just writing them down, just copying them, printing them out, make them do a little bit more work. Here's my intermediate. So same intermediate, I've got a methyl group in there now. So now
Why does the methyl group turn to a dash dash?
well, because I like to add the bromine from the top, but I can't figure out how to write a bold dashed bromine. So I intend the bromine to be on top. But if it was truly on top, then it would need a solid wedge. So my dashed line, interpret that as like a dashed solid wedge, even though that's physically impossible to write. So it just means that the methyl group's down. It's triangle sitting here, the methyl group has to go somewhere, it's going to go down. So in the end, the bromine's going to be on the bold wedge. And the water's going to add from underneath. But now the question is, where's the water going to add? Top carbon, bottom carbon, 50-50. Now, before we do that, let's just work with an acyclic one. Let's say I add my Br plus to this alkene. I'll call this carbon A, carbon B, carbon A, and carbon B. So it's easier to do what I want to do next with an acyclic system. So if I'm doing the bromohydride formation of that, and there's still going to be water in here, I'm going to form that bromonium ion as the intermediate. Now, next step is the water down here has to add to one of those two carbons. It's going to add either to carbon A, carbon B, or both. So the question is, where will H2O add? A, carbon B, or both? A and B. That's my question. Okay. I wrote the question on there because we have 2 extra people answering it from parts unknown. So I figured at least I would give them the question so they had something to answer with, something to answer instead of just randomly sending me an answer so they can get participation points, despite the fact that they're really not participating. This is a new phenomenon. They did this at 8 o'clock in the morning too, which is, they should probably get a couple points there. All right, is everybody in here answered? Okay. So we have 7 A's, 16 B's, and a C. All right, 7 A's. So B is the most popular answer. So now I have a question. If you answered B, why? Why do you think that the water is going to add to carbon B? Bobby? Okay. That the water is going to attack B because it has, and what does the more hydrogens mean? And we're talking about the water. So, anybody else who had B? Less sterically hindered. Okay, so water will add to the less sterically hindered carbon. Anybody have any other reason for voting for water adding to B?
Right.
What?
Right.
Okay. Gut instinct.
Yeah.
How about adding to A? What'd you?
Although it is attached to carbons, I don't know if that counts.
So water is going to add to the 2 carbons.
No, I just saw more features on the side. I don't know if it has to be directly to the
Okay. David?
Does that include the third degree carbocation versus tertiary?
Okay. So carbon A looks like a tertiary carbocation. Kind of, if you gave it a full charge. And the carbon B looks like a primary carbocation if you gave it the full charge. Usually when I do this, I like to get both opinions because you can approach this from either way. Right? That does not mean that A and B are equal in this case. It's either A or it's B. So let's talk about this from the standpoint of, let me ask this question. Which carbon, A or B, has the greatest delta positive charge? Hold on. Which carbon has the greatest delta positive charge? And I will give you a minute or so to discuss that with a neighbor.
They're not just reading the negative charge over their question.
Okay, your thoughts. What are your thoughts after discussion? Dylan?
Carbon A would be have stronger delta positive because the two other methyl groups attached to it counteract this pushing effect.
So stabilize it. Okay. Did anybody else have that reasoning for choosing A? Anybody? You had the same reason? Okay. Any other reasons for A? Anybody have a reason for B? No? Should have voted first. So that's correct. The two methyl groups on carbon A are going to be able to stabilize more positive charge than the two hydrogens that can't on carbon B. And if you take a look at this, and I put this in quotes, carbon B looks like a tertiary carbocation. It's not, but it looks like one. And carbon B looks like a primary carbocation, even though it's not. Exactly what you said. So which one of those is going to have the greatest positive charge? It's not going to be the primary carbon. So the tertiary carbon is going to have the greatest positive charge. Now, why is that important if I'm water, the nucleophile? Josh? Okay, it's going to be most attracted to the carbon with the greatest delta positive charge. Because this is kind of, we having a sense of deja vu about maybe particular kinds of reactions that start with SN? So what's an SN1 reaction driven by? Or what's its rate determined by? What kind of carbocation intermediate that it forms? Right? That's what drives its rate. Tertiary greater than secondary. That's why primary cannot do SN1. I'm water. What choice of reaction do I have? I've got to do SN1. Because as water, I am what kind of nucleophile? Weak. So because water is a weak nucleophile, it must do an SN1-like reaction. I know it's attacking from underneath, from the backside, but that's what gives it kind of an SN2-like feel. But the water is electron rich. It's not super rich. What did I say this morning? I said it was kind of like New York rich, right? Because New York's more expensive to live in than other places. So people that are rich there are just barely breaking even. But I am obligated to give my richness, my extra electron density to the poorest. And that's A. Okay, so I have no choice. Now, if I was a strong nucleophile, like OH minus, what would change? Potentially the mechanism would change, right? Because then I could say, oh, well, I'm a strong nucleophile, I can do SN2. And that's my preference. If I'm doing SN2, what's guiding me? Steric hindrance. So if I wanted to react at B, I don't want to basically put any charge, which I have no choice in this case, But if I want a triangular intermediate and I want to react my nucleophile at B, it's got to be a strong nucleophile. And it'd be best if there was no +1 charge on it. Because then I'm totally bound by SN2, and I'm bound by steric hindrance. Okay. So in this case, the water adds to carbon A, so I end up with the OH group here, and then over here, I end up with the bromine. And so that would be the final product of the final major product of the reaction. And so now what do I have? Now I've got a Regio selective reaction. And what you may be saying is, well, what if I just did the Br plus? What if I just add the Br plus to that double bond? What would happen? So let's ignore for the moment the triangle. If I added my Br plus, what carbon does the Br plus add to? Carbon A or carbon B? Okay? Want to change your answer?
Yeah.
B? So if I forget about the triangle and just treat the Br plus as if it was like an H plus, it's pretty clear where Br has to add. It's got to add to carbon B, right? Because tertiary carbocation versus a primary, I mean, we're not supposed to be writing primary carbocations. And then where would my water add? My water would add to the carbocation and then lose H plus and give me the final OH product. So if I would have done it this way to begin with, might have been more of the A's voted for when we looked at the triangle. But I like to do the triangle first because legitimately you could think about it, the water adding to either one of those two carbons from what we've talked about. Is it SN2 or is it SN1? Does it depend on the positive charge or does it depend on steric hindrance? But I'm going to go back to that triangle because the reason I'm doing this is because we need to deal with the triangle. We have to be able to determine where the nucleophile is going to add in a triangular intermediate because we've got at least 3 more triangular intermediates that we're going to deal with. And they all operate on the same principles that if it has an overall positive charge, the nucleophile is going to the most positive carbon. If it has no charge and it's a strong nucleophile, it's going to the least substituted carbon. Okay. So that's why I introduced this whole idea of working with the triangle. So we have to be able to do that, or at least get comfortable with it. Because and the other thing is, every time we have a triangle, we're going to have the possibility of stereoselectivity. Because every time we have a triangle, we're going to get 100% trans addition. And like I said, we've got a couple more. All right, so does that make sense? Sort of, not at all. Let me go back here. So Markovnikov only dealt with H's. He only dealt with H+. So the technical Markovnikov rule is that when you add H+, you add it to the carbon with the most hydrogens. And that is the strict Markovnikov rule. But I like to broaden it out a little bit and say, what's H+? It's the electrophile. So if the electrophile goes and adds to the carbon with the most hydrogens, that's an extension of Markovnikov's rule. So if we recognize in this reaction, in the Br2H2O reaction, that Br plus equals my electrophile equals my normal H plus, Br has to add to the carbon with the most hydrogens. Therefore, this is Markovnikov addition. And most of the time, Markovnikov addition occurs why? To form the most stable carbocation intermediate. Although I'm getting burned by that right now because we're looking at a reaction where it's going against the rules. And we don't know why, other than I suspected that would be the case. So I'm going to strictly say right now, instead of saying Markovnikov addition usually produces the most stable carbocation, because I now have one exception that keeps me from saying that, I would say, though, that your electrophile adding to the carbon with the most hydrogens is Markovnikov addition, and it doesn't have to be an H+. So to summarize for this reaction, what do we have? We have a Br and an OH, Markovnikov addition with the bromine going to the carbon with the most hydrogens, and 100% trans. And that would be the three characteristics of this reaction. Okay, so on Monday when we get back, we'll continue with reactions. This is going to be the last chapter we do this semester. We will start with alkynes next semester, which is okay but unfortunate because alkyne reactions are very, very much the same as alkenes, but that's okay. All right. If you have any questions about anything, you can shoot me an email. I might need some get away from family time, so I can certainly answer your emails.